Dear student, welcome to our course on dynamics of interfacial flows. I guess you ask yourself, do I need another fluid mechanics course? I just learned so complicated course on technical fluid mechanics. And actually my aim today not exactly to enter to the science of interfacial flows, but just to demonstrate you that actually you are missing important kind of flows which is necessary for many emerging technologies. And my aim today to motivate you and maybe to wake your interest to this topic, and I'm sure that if you will be this semester with me, then it will most probably influence your future career. Let's start with hydrodynamics of conventional technologies. This is actually what we studied in technical fluid mechanics, so let's see this just for fun in historic content. When it started, so it is very difficult to find, but what I found, for example, in the topic of atomization and drop impact, so people found rock art of cave people, so it is aged 10,000 years, so people just took mineral ink and sprayed on their hands. So what you see on this cave, these images of these hands, which are all left hands. So this is something people started to learn fluid mechanics and fluid flows in this way. Also irrigation channels. So this started 6,000 years ago in old Egypt and in the territories where today Afghanistan. So 60,000 years ago they started irrigation and they started to learn also to observe fluid flows. And this is more or less what we studied in technical fluid mechanics. Water clocks. So what you see is some old type of water clock of different shape. You know, some reservoir of specific shape with a hole inside, and the level of the liquid changes with time linearly. So the speed of height change of water in this water clock is uniform. And in technical fluid mechanics, so I guess that we learn this problem, you know that the shape must be actually parabolic. Okay, so there are also much more sophisticated water clocks. For example, what you see on the right image, the clock towers built by Susung in China, and actually all these water clocks, they already known for more than 3,000 years, or in this China this 1,000 years old. So this is actually more or less this time of technical fluid mechanics. So what you see is a very beautiful water clock in Science Museum in London. It's called actually clepsydra. Water wheel. So this is another well-known application of fluid mechanics, this conventional fluid mechanics, and you see it is already known almost 2,500 years. So starting in Egypt, Greece and China. Archimedes, this important, very important name, so you probably know him as a guy who invented, for example, Archimedes screw and many other things. So for us it is relevant legends about golden crown. So I'm sure you know it. You know what does it mean, Evrika, and you know this legend about force, Archimedes force applied to submerged body. So from this from this law, we know that if density of a body higher than density of the liquid, so the body will sink. So for in our future course, we will see that it is actually not always correct. But anyway, this is what we studied in hydrostatic, and it is known more than 2,000 years for people. Leonardo da Vinci, everybody knows his name, this well-known painter, but actually he was also kind of hobby scientist. So he observed nature, and among other, he observed some flows of jets. So now he becomes a guru for thermodynamic people, because it is very important to work imagination and fantasy for scientific creativity. But in fact, Leonardo. So what you see another his example of jets and vortexes. So this is what he was interested. And among other things, Leonardo once formulated law of mass conservation of mass. Okay, so this is something which is known already around 500 years, but unfortunately his inventions were forgotten, so this law was forgotten and then reinvented again. But we are thankful to Leonardo da Vinci not only about his laws, but also for his paintings and for his creativity. Bernoulli. So we know Bernoulli from Bernoulli law, from technical fluid mechanics. Actually, it was not easy to find the correct Bernoulli, because its name belonged to many talented people, and this is Bernoulli equation. So it belonged to Daniel Bernoulli. This is Swiss scientist. So among other, he invented a device for measurement of the blood pressure. So you see this example actually. So you need to measure blood pressure with his apparatus, you need to make a hole in your body, and then you just really measure in the glass tube, you measure the height of your blood, okay, to measure the blood pressure. Okay, so this actually, I am very thankful to this modern science which invented modern apparatus for blood pressure measurement. So what we know about Bernoulli is his well-known Bernoulli equation, and we like this because this is not one of these equations which help us to solve real problems. Okay, but it is often happen in science that actually the final form of this equation have been formulated not by Bernoulli but by his student Leonhard Euler. This is also a Swiss mathematician, and he removed limitation for steady case of Bernoulli equation. But don't worry about Euler, so he left his name for history and for us. So his name is also well known. So another important person for us is Newton. From his name come viscosity and Newtonian fluids. But among other things, he invented calculus. So he formulated 3 laws of classical mechanics, and also he studied nature of gravity. So this is the same person who introduced Newtonian liquids and concept of viscosity. Also, kind of at the top of our course of technical fluid mechanics, there is Navier-Stokes equation. So as you see, it is beginning of the 19th century. And this is actually top of our course of technical fluid mechanics. So this Navier-Stokes equation is named after French and English scientists Navier and Stokes. But actually, scientists discuss about their formulation, and it seems they didn't understand completely the meaning of the equation, but the final understanding and final form belong for Navier-Stokes equation belong also to actually to other guy. Its name is Cauchy. Okay, so but this is also beginning of the 19th century. So this equation today is used for computation of many industrial flows, for example, aerodynamics, car dynamics, internal combustion flows, and so on. Many other flows are computed using Navier-Stokes equation. So one of the topics also biological flows. So, for example, flows related to our health, flows related to the motion of animals, of fishes or birds. Actually, so people who pay for the study are military. So you know that engineers develop some devices which imitate flows of natural objects. So all these flows are used, are computed using Navier-Stokes equation. So most of existing flows can be computed using this equation, so and they don't need any additional physics. But this equation, what you see, it is actually 200 years old. And I ask myself, well, whether hydrodynamic didn't develop during last 200 years. And actually our course is aimed to fill this gap to the modern fluid mechanics. Another important name is Osborne Reynolds. So this guy, you know his name, yeah? You know this name. So he investigated regimes of flow in the tube. So what he found that the transition from the laminar flow to the turbulent flow happens at specific conditions which are described using dimensional number which is known today Reynolds number, which is the ratio of the inertial forces to viscous forces. I hope you understand my point. What I want to say is that the topics which we studied in the course of technical fluid mechanics, they are mainly 200 or 1000 or maybe 3000 years old. But there are many different topics of fluid mechanics which developed during last years, and they continue to develop. And one of these important fields is interfacial flows, which is rather important for many future technologies. And this will be the topic of our course.